Welcome to the assignment 4 instructions for ENVR1190 Data Management at Niagara College. This assignment is working with weather data, and we're going to be practicing linear regression. So the data set that we have is downloaded from climatedata.ca, and it is for Toronto Lester B International Airport from 1937 until 2024. These two data sets are just separated because they changed the name of the station. So if you go into this data set, you'll see that we have 31,000 lines and we have 36 columns. And within each of these, we have the daily weather at this weather station. And there's all sorts of different measures like precipitation and temperature and all these other wonderful things. And so what we want to do is look at how the annual daily minimum, maximum, and mean temperature has changed through time. And so we're going to do that by condensing these into measures of each year. And so the best way that we can do that is to make our wonderful table with Control L. We can change our name to weather for this table. And then what we can do is right click and bring it into our Power Query with the Get Data from Table Arrange. You'll see that I have some other ones here that have all been practices. I'm just going to delete those. So with our Power Query, the first thing that we want to do is choose the columns that we want to keep. And there's only a few that we actually need to keep, so we can unclick all of the columns and just select the ones that we want. And the ones that we want are minimum temperature, mean temperature, max temperature, and local year. And so now we've gone from that big, busy data set of 36 different columns to just the 4 that we actually need for our assessments. Now, one of the steps that we missed in class was filtering out these incomplete years, which kind of screwed us up when we were doing some assessments. And so what we can do is we can unclick 1937. And if we scroll down, it says that this list is incomplete. So all we have to do is click Load More. And then we can see that we don't want 1937, which is incomplete, and we don't want 2024, which is incomplete. And then we just press OK, and it adds this step where it says, I'm just going to exclude those on any of those rows. And so that makes it so that we can actually do our assessments on full year's worth of data. The next step that we're going to do is to group by the local year so that we can get the averages of each of these 3 measures that we have. So we group by, and we go to advanced so that we can get multiple columns. We already have local years selected, which is the one that we're going to actually group by. And then we're going to create 3 different columns that take the average of each of our different measures. So we're going to have one for the max, one for the mean, and one for the min. Now you can see that we have only 1 row per year for each of the 86 years. And we have the average of each of these measures in that year. And that's going to allow us to see how this might have changed through time. With that, what we can do is simply close and load. And we'll call this all temp, so that we have all of the temperature measures here. What we did, the one graph that you need to have for your actual assignment is a scatter plot that has all of these in it. And so we can simply go to scatter plot, and because we've set up our data in this way that we have our independent variable, our x variable in the first column, and then we have these 3 dependent variables, our y variables, in columns after it. Scatter plots can recognize that in Excel, and it recognizes that we want to be plotting the temperature by time. And so this is our basic standard format, but there's a few things that we know that we want to do to edit this. And so the first thing that we can do is get rid of some of the things we don't need, like chart title and grid lines. And then we can add things that we do need, like our axis titles. And so here we have our year. And then on the y-axis, we have our temperature in degrees Celsius. We can also, so the way that the editing works for the charts is that whatever segment you click on, you'll see that this panel pops up, and then whatever you're on, you'll see that the options are there for that. It's worth exploring this a little bit to see kind of how you can change these different things, but for most of them, there's these kind of three main things where you can change the colors, you can add effects to them, which you usually don't need to do, or you can change the actual graphic series options for it. So here, when we're in these options, you can see that there's all these different things that you can change that are associated with it. And so for our x-axis specifically, let's just go in and change our minimum bounds so that it's more round numbers near where we actually are instead of these white patches on either side. And so we know that we start at 1938. So let's just start at 1935, which is a nice round number near that one. And you'll see that that adjusts there. And then what we can do is we can adjust to a nice round number near where we are now. So let's just pick 2025, which is another multiple of 5. That's right on the edge of that. Perfect. One of the other things that we can do is change our legend. And so by going into these options, we can pick which side we want our legend to be on. And so for this case, I think it looks best if it's on the right. That way you can see that the max, the mean, and the min are kind of corresponding to these different colors. We can also start to add our trend lines. And so when we first click this, it's going to say which trend line, which series do you want to add a trend line for? And so we can start off with max, and you'll see that now it has this line that's there. If we do it again and we go from this little side arrow to linear, we can add it again, and we can just add one of these trend lines for each of these series. And what a trend line is doing is a linear regression, which is exactly what we're trying to do here. And so again, the difference between a linear regression and a correlation is that we're trying to determine how much our independent variable, year, is actually causing our dependent variable, temperature, to change. And so it's not just looking at how it varies, we're actually performing a test and we're creating a equation that says this is the relationship between these two things. And we can use that to predict things, unlike with correlations where we're just looking at how they vary together. So in terms of these aspects of our plot here, we can double click. Once we're in the legend, if we click on any of the individual elements, we can highlight that one specifically. And if we press delete, we can just get rid of each of these lines, which we don't actually need to have. And then this is starting to look pretty clear about what we're trying to say. The way that we can get at some more information from this linear regression in our scatter plot is to go to this graphical thing here. For the trend line options when we have trend lines highlighted, and we can go all the way down to the bottom and we can display the equation on the chart. If we click on it again, we can move it so that it's in maybe a better spot to look at. And if we go to our home tab, we can actually change the color of it so that maybe it matches our colors so that we actually can see it a little bit better, and we'll make that bold with Control B. And we'll do that for each of these so that we can display these equations that the linear regression is coming up with for each of these different variables, or for each of these different dependent variables. And we will, well, that's not the right color. This is the right color. Great. So this is the one figure that you need to include within your report. And you can see that each of these equations is slightly different. And so there's a couple of key things when we're thinking about our equation of a line, which is y equals mx plus b. And so you have a sheet that can tell you kind of how these work. But what each of these equations is telling you is that y, which is our dependent variable, is equal to some number, some slope times x, which is our year. And so what this number is telling us, our slope is how much temperature increases with each year increment according to this line. And you can see that this one, 0.01, is less than 0.02, which is less than 0.03. And so what this is telling us is that the minimum temperature is increasing slightly faster than the mean temperature, which is increasing slightly faster than the maximum average daily temperature as you look at it through years. And so what we aren't doing is actually comparing these to see if they're significantly different from one another, but we can see that they are practically different from one another. And so we're not actually comparing these to look at if, statistically they're different from one another, because we're basically doing 3 separate linear regressions here that aren't necessarily related to one another, but we can see that based on these results, it looks like there's this trend where the minimum temperature is rising faster than the mean, which is rising faster than the max. The other piece of information that we can see here is the y-intercept, and that's our b. And what the y-intercept is telling us is what is the value of temperature at year 0, because this is just treating year like it's a number. And so it draws this line all the way back to year 0, and it says, what would temperature be at year 0? And so for each of these, let's just look at min, which is the example that we did in class. What this model that we've created is telling us is that at year 0, so about 2,000 years ago, the average daily minimum temperature would be minus 62.8 degrees Celsius. Now think about that for a minute. What does it mean for 2,000 years ago, the average daily minimum temperature being minus 62 degrees? That's real cold. And that's also kind of ridiculous to think about. But that is what our model is telling us. And so the piece of information that we're kind of missing is that this model is assuming that this straight line goes back all the way through time, when there's really no reason to believe that that's true, because we know that temperatures have started to increase more since the Industrial Revolution in the 1800s. And so when we're thinking about using this model, we have to think about what does it mean instead of just what are the numbers telling us. And so this means that if we followed this straight line all the way back in time, and temperature was consistently increasing at a rate of 0.03 degrees per year, that would have meant that year 0 had an average daily minimum temperature of 62 degrees Celsius, which is absolutely ridiculous. But what we can start to think about is if temperature increases at this rate moving forward, what would temperature be in a matter of years? And that's actually a pretty reasonable question to think, like, if we're actually increasing at this rate pretty consistently, like it appears that we kind of have been over the last 86 years, then what would temperature be in the year 2100? And so that's actually a more reasonable extrapolation of these results. And that term extrapolation just refers to how you are expanding beyond the sample that you have to make predictions about your population, right? So again, this is the figure that should appear in your reports with an appropriate figure caption that explains all the different things that we're seeing here. But there's limited information that you can actually get based on the linear regressions that you do with the scatter plot in Excel. And so that's why we're also doing this in a more regimented way to use the data analysis tool. And so to start on doing that, let's go ahead and start to do each of these on their own sheet individually. So what we can do is copy the sheet, and it's easy. You can just go move or copy, or you can hold Control when you're hovering over this, grab it with your mouse, and then move it to the side to make a copy. And it's going to call this all temp 2, but we're going to do the minimum together. So we know that we just want to do minimum here. So what we can do is delete these 2 columns for max and mean by grabbing the B and dragging over. And we can just click delete. And so now we only have the minimum on this graph. And we have we can move this over to the side so that we can start to use some of our data analysis tools right beside it. Yeah, so we can exit out of there, move it something like that. So the first thing that we're going to do is we're going to practice using our descriptive statistics tool again. So we go to our data tab, we go to data analysis. And we have to pick which one we want to use, and we're going to create the descriptive statistics. So it asks us what our input range is, and we'll just highlight this whole table. And that was by grabbing this one, pressing Shift to the right, and then Control Shift down. We tell it that we want to group by columns because that's where our values are. If we picked rows, it would summarize by year, which is just this one value. And we tell it that we have our labels in our first row because we have the names of those columns. Now we tell it where we want it to output, and we're going to put it just right beside our table here. We have to pick what we want, and so we pick just the summary statistics. Now, some of the people in class were like, how do I get it so that I can actually see all the values? So if we go to the Home tab and we go to Format, we can auto-fit the column width, and that's going to allow us to see all these different things. And so as kind of a test to yourself, I want you to kind of look through these and see what it is that you actually understand about some of these different values. For example, why is there no mode, right? It has this hashtag NA for mode. And so think about what mode is and think about why there might not be a mode there. We can also use this as a way of kind of assessing the values that we have. And so we know that our mean and median year are around 1980. And this in class is a good way to actually see if we are getting different results from someone else that is doing this, right? And so some people were getting counts of 86 because we had forgot to filter out those 1937 and 2024 years and had different ranges. And so this is a good way to kind of assess your data and say, do these values make sense? Does it make sense that for the average daily minimum within each year, our minimum value is 0.74 and our maximum value is 5.78? That seems to make sense to me. And we have this range of kind of 5 degrees here. And we can see that on our chart here where we have our minimum and our maximum. And we can start to understand more about the way that our data are distributed, such as looking at this kurtosis and skewness, which are things that we haven't looked into too much, but are related to the normality. We can start to look at how the variance, standard deviation, and standard error that are associated with these. And again, remember that these are related to each other, and where our variance is always the largest, and then we take the square root of the variance and we get the standard deviation. And if we then take the standard deviation and we divide by the square root of the count, that's how we get to our standard error. And so variance is always bigger than standard deviation, is always bigger than standard error. And the key thing here is that our standard error is when we're getting into the inferential statistics side of things, and we're trying to predict what is the error around our population mean, moving away from our sample mean. So again, these are all a lot of numbers, and you could do these by just calculating mean and then doing the average of, you know, this thing here, and you're going to get the same value. But it takes a lot longer to do that than it does to just go to our data analysis tool. A fun thing that I've found recently is you can also just do this, where you click this insert function, and it says, which function do you want to use? Let's just start that from scratch. So we click the function, and it says, what do you want to use? And we can pick average, and it'll give us these options of different things that we can do. And then we pick that, and it allows us to just enter in the values that we want to do. And lo and behold, we get the same mean that we have there. But that's kind of 3 different ways that we can get at some of these values, but this way is probably the quickest and the easiest and the most repeatable. The next thing that we're going to do is our linear regression in order to start thinking about our how this model that we created, which is the same linear regression here, if it's statistically significant. So I'll just write this down. So now we're going to use the data analysis tool to look at 1, if the model is statistically significant, and 2 if we've met our model assumptions. And these are things that you can't get with just the scatter plot model. So let's go ahead and go back to our data analysis tab, and we'll go to regression. And then we will click OK. We can input our Y range, and our Y is always our dependent variable, so the thing that depends on the other one, which is our minimum here, our temperature. And our X is always our independent variable, the thing that we think is affecting the other thing. And so we click labels because we have those. We choose our output range, which is going to be down here. And we pick the things that we want it to output with. And so in this case, we want to actually look at our residuals and our normal probability. And so what we're going to do is click all these and the normal probability plots. We click OK. Now you'll see that we have these plots that have popped up that allow us to look at our model assumptions, and we have all of these different outputs that have kind of come out of our model here. So there's a couple of things. This is a big amount of information that we have that's come out of here. I'm just going to show tabs only there. And so, but there's a couple of key things that we want to look at. And so the first one is our R squared. Now you can actually get this from within our scatter plot. And so if you click on your line again, you can display R squared value on chart, and you'll see that the R squared of 0.42224 is the same as the one that we have here. But the thing that this is showing us, let's just make this a little bit smaller, is the R squared is an important thing to look at in linear regression because it tells us how much of the variation in our dependent variable is explained by our independent variable. And so you can think about it almost like a proportion. So in this case, what we're saying is approximately 42% of the variation in temperature is explained by year, which is pretty good when you think about how much variation there is in temperature and how many factors are actually influencing it. And so a couple things about this R squared number is it ranges from 0 to 1, where 1 explains everything and 0 explains nothing. It's also related to our correlation coefficient, which is often called R. But it's just the square of our correlation coefficient. And so it's all related to that relationship between these two variables. And then there's these other kind of attributes of R, but this is the one that we're looking at right now for a very simple linear regression, and also has our number of observations there. So this is the first number that we want to look at in terms of our summary output to say, well, how good is this independent variable year at explaining our dependent variable temperature? Then what we can do is we can go down to this ANOVA table. And there's a lot of information here, but this part up here is basically telling us a lot of the information that it's used to actually fit this model. And this isn't actually too important for our purposes in terms of being able to interpret the things that we want to get at, which is it statistically significant and have we met our model assumptions? And so what we can do instead is we can go down to here where we have this table and it has intercept and local year. And so what these are is this is our y-intercept E, and this is our slope M when we're thinking about y equals mx plus b. And so we have these two values here, which are our coefficients, which are the same as we get when we look at our scatter plot, right? We still have this 0.03 slope, and we have this minus 62.8 y-intercept. So again, what this is telling us is that each year it's going up. Temperature is going up by 0.03 degrees. And that if we go all the way back to year 0, the minimum temperature would be minus 62.8 degrees, the average daily minimum temperature. And we've discussed how that's kind of ridiculous, extrapolating all the way back to 0, but that's what this model is telling us. Some of the other things that we're going to look at when we're here are related to our standard error. And so the standard error, again, is that measure of variation that the model's coming up with for how it's confident in these different things that it's put together for this linear relationship. So what this means is that local temperature is increasing. So this is telling us the slope related to year. And so this is telling us that our, average daily minimum temperature is increasing by 0.03 degrees each year. And then it's telling us that the standard error is plus or minus 0.004 degrees. And so in terms of the way that it's predicting our model, it's saying that the actual slope could be 0.033. So that's kind of the best model that we have, but it could also be 0.33 minus 0.004, which is 0.29, or it could be 0.033 plus 0.004, and then it could be that high. And that's what it would think that that's what our model thinks that this slope is with 95% confidence. And so and there are some other confidence that are intervals that are here, and those are important for kind of understanding, again, the range of values that we're being able to estimate for this one. And so these are related to confidence intervals. But the last thing that we really need to understand in order to just interpret the things that we're hoping to get at, which is our model statistically significant, are these p-values. And so this e to the negative 11, again, means that this is, you move this decimal place 11 places over here. And so this is actually a really, really, really small number. And what that means is that the p is less than 0.05, which is our cutoff. And so each of these, with each of these, we reject the null hypothesis. And so for each of these variables, the null hypothesis is that the value is 0. Because again, we're assuming that when we're doing our hypothesis testing, that basically nothing is going on, and then we're trying to provide evidence that something is going on. And so our alternative hypothesis is that the value is not 0, which means that the intercept is not 0 because the p-value is less than 0.05, and the slope is not 0 because the p-value is less than 0.05. And so when we're thinking about a linear regression, this means that there is some explanatory relationship of year in terms of its influence on temperature. And we have high confidence that that is actually happening and that it's not 0. So we're able to reject our null hypothesis and provide evidence for our alternative hypothesis. So that's this one done. And so now we have that done. We'll just call that green. So we can verify that we reject our null hypothesis and that our alternative hypothesis that there is a relationship between, or an effect of year on temperature. That's how we know that this is statistically significant. Now what we can do is check our model assumptions. And the way that we can do that is to start looking at these other plots that have popped up. So our model assumptions are, let's just continue to be messy over here, and we'll write 1, that there's a linear causal relationship. And we can confirm that we do think that there's a linear causal relationship that's associated with these, right? Because we do think that time has some impact on temperature, given that what we know. The second one that we're assuming is that there's independence of our observations. And so basically what we're saying is that the temperature in 1939 is independent of the temperature in 1938. And so that's not explicitly true, right? Because you can also see that when we look at this scatter plot, we have this kind of weird relationship where it seems to go up and then kind of comes down in this like looping pattern, and then it kind of goes back up again. And it's not exactly this straight line. And so this assumption of independence is not explicitly true, but it's important to recognize that that's what our model is assuming, is that each of these years are independent. And so we know that there's a little bit of what would be called collinearity between, or so each of these is kind of related to the year before it and maybe the year after it. But in this case, we know that approximately there will be independence between our years. And so we're treating them like they're independent of one another between years. The third thing that we need to assume when we're doing our the third thing that we need to assume is that we have normality of our residuals in our model. And so what our residuals are is essentially the error that is not explained by this line. And so if we zoom in, each of these points, so let's just pick this one point right here, is away from this line in some way up or down. And so this one, what the residuals are doing is it's saying for each of these 86 points that we have, how far away is it from the line? And then so in 1930, that looks like the second one there, so that would be year 1939. What we can do is we can go down to our residual table and we can say for observation 2, how far away is it from the line? And it says that it's 0.41 degrees away from the line, which seems to make sense when we just look at it. And so this whole table of residuals here for the 86 years that we have is telling us where does it fall relative to our lines. And what we're assuming is that these residuals are normally distributed. You know, you have lots of them that are around a certain value, kind of centered in the middle, and you have very few that are either really, really small or really, really big. And what that looks like should be somewhat of a shotgun blast around this line. And we can already tell that there's a little bit of weirdness that goes on with this kind of cyclic nature of the temperature. And so kind of as we were getting at with our independence of observations, we're rarely going to have perfect data that fits these models that we're using. But it's important to understand what the models are thinking in order to be able to interpret them pretty properly. So the way that we can look at these normal probabilities, this kind of distribution of the residuals, is to look at this normal probability plot. And if we just add a trend line, we can kind of see where the residuals differ from this line. And if it's perfectly normal, then it's going to be just along this line the whole time. We can see that we have some minor deviations that kind of go along with that cyclic nature of the data. But all in all, we have kind of a pretty reasonable adherence to normality that's associated with that. Now we can look at that with our normal probability plot, but another way that we can also look at that is just to plot the residuals. So if I click on that title there and I do Control-Shift down, I can insert a histogram. And we can see that we kind of have a little bit of weirdness, right, where there's kind of this bulking in the center of the data. But in general, we have pretty good distribution of our data where we have a lot of it kind of in the center and then it kind of goes off towards the sides a little bit. And so I wouldn't think that this has any reason for us to reject the models that we're using and try and use a different kind of test. I think that we have some deviations from normality, but all in all, the data adheres pretty well to that as an assumption. The final assumption that we need to test is our homogeneity of variance. And so basically what we're looking at is the data more variable at one end of the, is our dependent variable more variable at one end of our independent variable or from the other? And so again, what we're kind of looking at is this shotgun blast of data across. And we can see that we don't really have a lot of data here, and we're kind of missing this chunk here. And that's because of that weird kind of cyclic nature that we're getting to our data around the 1960s. And so we can already see that we have a little bit of weirdness that's going on with our variance. And the way that we can also kind of check that out too is this local year residual plot. And so when we're looking at this one, we can see that we have some residuals that are a lot higher in this area, and then around here we have a lot of them that are lower, and then it kind of is almost more evenly distributed across over here. And so this isn't exactly what we want to see, because basically what we would like to see is for it to be a shotgun blast across all of these values, right? Where we have a really even distribution of residuals across all of the values of our independent variable year. And so we're not meeting this very well here, but we do have a pretty good distribution of residuals through time here. And so we can be aware as we're trying to interpret these results that we have this kind of cyclic nature to time, which causes some minor deviation from our assumptions. But all in all, it doesn't seem like this should be something that really too influentially affects our results when we're thinking about just this linear model that we're trying to come up with here. And so all in all, I think that we can understand that we have some minor deviation from these assumptions, but all in all, it's not likely to be affecting our results in our interpretation too much. And so then we can look at all of the things that we've discussed here, and we can say that these are really good ways in which we can kind of understand the model that we've created in a lot more detail. So just to go over this again, the reason that we're doing this output, even though it's the same as our linear regression, is to, from the scatter plot, is to look at some of these other things. And one of those is the R squared, which tells us what proportion of the variation in temperature is explained by year. It's to look at the levels of confidence around our coefficients, so our y-intercept and our slope. And then it tells us what the significance of these is in terms of being different from zero. And so if we were to just look at this line, we wouldn't know if it's significantly different from zero. But because we've done our linear regression output, we know that it is statistically significantly different from zero. We can also use these outputs to test our assumptions and to see how well we meet them. And so what we've determined here is that using our normal probability plot, we can look at the deviations away from this straight line, and we can see that there's some cyclic nature to the data that deviates from normality. We can look at that a second way by looking at our histogram, which shows us that we mostly have this kind of centering with little distribution of the data towards the tails, but there's definitely a little bit more bulking towards the middle of our model. And then so that's how we can check normality. And then the way that we're checking our other assumption of the homogeneity of variance, which again, homo is just the same, thinking that it's the same variance across, is by looking at this scatter plot through time, of time, and then looking at the residuals. And we can see that there is some weird cyclic nature to the data, but all in all, it's kind of pretty well distributed across this range in years that we have. And so what we need to do for the rest of the assignment is to do this with the other two variables. So you can, again, copy this sheet and start to do all of these things again. And the thing that you need to be putting into your final report is this figure here, and then explaining what these relationships mean, talking about our adherence to the assumptions, and then thinking about what direction we can actually extrapolate this data. And so there's room to interpret this how you will and include the information that you think is interesting and relevant, but try to focus on what these data actually mean and what we did.